For the rest of the day today, let's talk about inner product spaces with an example. Let's let our vector space V be a space of functions. C of some interval is the typical example we think about. I think for the homework, it goes from 2 to 5. Let's pick over 0 to 4 here. What is that symbol? It's a vector space, meaning as a purely abstract algebraic idea, the elements of this, you could call them vectors, satisfy all the vector space properties from, what was it, about a month and a half ago, where you were introduced to it? Things like the associative law and the commutative law and the distributive law for vector addition and scalar multiplication, that kind of stuff. There's a zero vector. But this is a particular vector space. It's not just, and it's not an abstract one, though it's still kind of difficult to wrap your mind around. The vectors in it, the points, if you prefer, are functions. The individual points in this space are functions, like t squared or cosine of t or e to the t. Those are all examples of functions that are continuous on this interval. Why did I pick this interval? Just because I felt like it. I could have picked something else. Just a random interval in my mind. I chose the left endpoint to be 0 to make the integrals a little easier to do. The points, the vectors themselves are functions. T squared is one vector, one point in the space. Does that mean its graph is in the space? Not technically, no. It's that one function as an idea, as a mathematical object. That thing is one element of this space. But it's more than just a vector space. We also call it an inner product space because you can define an inner product on it with a certain funny notation. F comma G with these pointy brackets around it is pretty standard notation for an inner product of two functions in this case. Some people don't use pointy brackets. Some people use parentheses, but I think using pointy brackets is better. The idea of an inner product is it's supposed to generalize a dot product. And these kinds of function spaces, you use an integral to generalize a sum. And instead of multiplying individual components of finite dimensional vectors, you multiply outputs of the functions, f of t and g of t. And you integrate over whatever the interval is that you're talking about. In this case, 0 to 4. Is this the only inner product I could define on this? No, actually, there's probably infinitely many answers, I believe. Infinitely many inner products you could define. This is just the simplest one. Why would we want to define inner products? It depends on what your application is. You design the inner products to fit the application. And thinking ahead to this ideas with Fourier series and partial differential equations, which is going to be our main application of this idea. We're designing the inner product so that over the intervals of interest, which typically are like negative pi to pi or 0 to 2 pi, our standard trig functions, cosine of t, sine of t, and higher level frequencies of those, cos 2t, sine 2t, cos 3t, sine 3t, end up forming what's called an orthogonal set with respect to this inner product. They are all orthogonal to each other. Not that their graphs intersect in a perpendicular way. To get to that, it means when you compute this inner product for like cosine of t and sine t there and there from say 0 to 2 pi, you integrate it, it integrates to 0. And so in the abstract function space, somehow those points in that space are at right angles to each other. Are they literally? Not literally, because you can't really visualize it literally. We can only sort of pseudo-visualize it, but that pseudo-visualizing is still helpful. In a way I'll describe very shortly, actually. Yeah, what's the inner product of, say, t and t squared, you could compute it. Integrate the product of those things, t times t squared is t cubed. Do this integral, you're not going to get 0. 1/4 t to the 4th from 0 to 4, you're going to end up with 4 to the 3rd. In the end here, you're going to end up with 64. Not 0, these are not orthogonal in this inner product space. Positive, the angle between them is less than 90 degrees, maybe. I'm not going to try to draw it. I could do plenty of other examples there. This has all the same kinds of abstract properties that dot products have. The funny brackets with the comma acts just like the dot in between them. It's weird notation, weird ideas, weird terminology, but these are standard things. But yeah, it's like you're adding, the integral's like adding up a bunch of products, like components of vectors, but these are essentially infinite dimensional vectors because they have infinitely many outputs, whereas individual finite dimensional vectors, in effect, if you have a vector in R3, it's got 3 outputs. The components are the outputs, so to speak. A first component, second component, third component. It's like you could think of that as a function where you plug in 1, 2, and 3 for the first, second, and third spots, and the whatever numbers are in the first, second, and third places are your outputs. You could think of vectors as being functions. Blow your mind? Again, it's still a question of whether that's a useful thing, but you could do it. If I put a negative t squared there, I'd get a negative 64, and the angle between them would be bigger than 90 degrees. Okay. What do I want to do here for the rest of the day here still? I want to try to help you understand the purpose of all this again. Let's let W be the span of, say, the functions 1 and t. That 1 is not the number 1, it's the function 1. Function whose output is always 1. If it were a solution of a differential equation, it would be an equilibrium solution. By the way, these are polynomials as well, so you could think of this as being a subspace of a space of polynomials. But they're also functions. You could think of it as being a subspace of V here. They are continuous functions on this interval. It's a two-dimensional subspace. These functions are not scalar multiples of each other. They do form a linearly independent set. This would be a basis for W. We're interested in finding an orthogonal basis for W. Why? Because once you got an orthogonal basis, formulas are simpler. That's why. That's really the benefit of orthogonal bases. It makes formulas simpler. It's kind of like a change of coordinates making a formula simpler with differential equations, changing to new variables u and v instead of x and y by diagonalization. It's a problem-solving tool. It's a way of thinking about differential equations that makes solving them simpler because they become diagonal matrix, for example, completely decoupled system, simpler to think about. And then you got to transform it back to the original system. So this is a basis for W, but not an orthogonal basis. If you take the inner product of these two functions, you don't get 0. What do you get? You get something non-zero. Integrate 1 times t from 0 to 4, you're going to get integrate t. 1/2 t squared from 0 to 4, that's going to become 8. Okay, their inner product is 8. Main thing is it's not 0. How do you find an orthogonal basis? And why would that be a good idea? You can use the Gram-Schmidt process. And you could even try to visualize it. similar to the Gram-Schmidt process for ordinary vectors. I always do find it difficult myself to memorize the Gram-Schmidt process. I did review it before class today. Thinking about ordinary vectors that are arrows, call this vector x1, this vector x2. I'm drawing this in the plane of my paper, but you could pretend these are vectors in three-dimensional space if you like, though they would lie in the same plane. They would define some plane. You could let W be the subspace spanned by x1. And you could also note that x1 and x2 together would form a basis for some two-dimensional subspace. It would be the entire plane if these are vectors in R2. It would be some plane to the origin if these were vectors in R3. But it's not an orthogonal basis according to the usual inner dot product because this is not a right angle. How do you make an orthogonal basis? The algorithm, the Gram-Schmidt algorithm. Oops, I forgot an H. Schmidt. Gram-Schmidt algorithm. SCHMIDT is what that's supposed to say. Says, okay, let V1 be the same as X1. So effectively, X1 becomes the first vector in your orthogonal basis. And let V2 equal X2 minus the projection of X2 along W. What's the projection of X2 along W? Draw a perpendicular down here. Right angle there. This vector right there would be the projection of X2 along W. And if we subtracted from X2 itself, thinking about how you add vectors visually, its opposite would get added. So if you draw it up there, draw a vector pointing that way, that's going to be the opposite of the projection. Doesn't matter where I put the tail of the vector. I can put it up there if I like. Then the sum, X2 plus this thing, which is the same as X2 minus this, is going to start here and go to there. This is going to be V2 right there. And you can see it's orthogonal to X1, which is the same as V1. V1 and V2 are orthogonal. Expanding this formula a bit, oops, not X squared. X2, this projection is going to be found with dot products to be X2 dot, I could call it X1, but I'll call it V1. Right? The usual kind of projection formula. So I don't know, I find this Gram-Schmidt process hard to remember. I always want to review the formula, and it can apply to higher dimensional situations as well. The algorithm can go further. And it's not too hard to understand based on the picture if you understand your basic concepts about how to add vectors and how projections work. But what I want to just say is you can apply this algorithm to inner products as well, inner product spaces, to create orthogonal bases for inner product spaces, like for this W here. And if you want to, you can visualize it like this. This picture is not a literal visualization of what I'm about to do, but it's kind of a visual for inspiration, you might say. You could pretend these things are functions. If you pretend they were functions, you'd probably more think of them as points. And this would be the zero function here at the origin. Not that you couldn't think of them as arrows if you wanted to, but maybe that gets more confusing. The picture can still serve as inspiration to help you believe that this still works, though you still have to verify all the algebraic details that you really do get an orthogonal basis for it. So if we try to apply these ideas for this example, Okay, I'm not going to use V1 and X1. Let's call this F1 and F2 maybe. I won't use a new letter here. Okay, so F1 equals the constant function 1 is going to be the first quote unquote vector in my orthogonal basis. That's nice and simple. What's F2 going to be? I won't call it V2. According to this pattern here, it's going to be, oh, and I don't want to use it. Okay, sorry. I don't want to call it F2. I want to essentially use this formula here. X2 will become F2. And V1 is the same as F1. There's supposed to be a minus sign there. And change the dot product to an inner product. It's not traditional to put the t's up in these functions here. I could, it's not a real big deal. Don't let it confuse you that I'm putting t's here and here, but not in there. It just gets messy if you do. I got to find these inner products. And once I've simplified this, I'll have a new function that's supposed to be orthogonal to this one with respect to this inner product right there. Let's go ahead and do it. Let's find these inner products. Inner product of F1 with itself means the inner product of 1 with itself. Integrate 1 from 0 to 4. Get 4. Inner product of F2 with F1 means inner product of T with 1, which we've already computed. It was 8. So this new function, should I give it a different name? Maybe I'll call it G2. Is going to be F2 of T, which is T, minus 8 over 4, which is 2, times 1. T minus 2. That's what it simplifies to. This should be orthogonal to 1 in this inner product space. Is it? Try it. Take the inner product of 1 and T minus 2 with respect to the inner product. So integrate the product of these two functions from 0 to 4. You can see, hopefully already, that is going to have a net area of 0. It does integrate to 0 if you want to see it by actually doing the details. You get 8 minus 8 in the end, you get 0. So 1 and T minus 2 are orthogonal in this inner product space. They form an orthogonal basis. Do they form an orthonormal basis? No. I'd have to normalize them to do so. How do you normalize a vector? You divide by its length. What is the length of these vectors? Length is probably a bad word to use. Magnitude is probably better. Norm is even better. I taught use the word norm in the lectures. I'm not gonna. Okay, maybe I should normalize them just to over here. The notation once again is double absolute value signs. When you find the norm of a vector in an inner product space, you take the square root of the inner product of the vector with itself. Just like with ordinary vectors, you take a square root of the dot product of the vector with itself. We already found the inner product of 1 with itself. It was 4. Isn't this a weird looking equation? The norm of 1 equals 2. Weird looking, don't misinterpret it. That's not saying that 1 has an absolute value of 2 in the ordinary sense. It's saying the norm or size or magnitude of this function in this inner product space is 2. It's always with respect to whatever the inner product is. If I used a different inner product, which I could, I'd get a different answer. Which one's right? They're all right, mathematically speaking. The bigger issue is which one's useful. What about the norm of t minus 2? It's the square root of the inner product of t minus 2 with itself, which I haven't done that yet. Square root of the integral from 0 to 4 of t minus 2 quantity squared. You could expand that. You could also do a quick substitution here. U equals t minus 2. du is dt. I'm doing calculus here. Change the limits of integration. When t is 0, u would be -2. When t is 4, u would be 2. Got to do that integral. Actually, it's an even function, so I could make quicker work of this, but looks like it's going to be in the end square root of 16/3, which would be 4 over the square root of 3. A little bit bigger than 2. You'd want to divide these functions by those numbers to find an orthonormal basis. An orthonormal basis would be 1/2 1 divided by its norm of 2, comma, t minus 2 over 4 over square root of 3. Which you could write like this. This is an orthonormal basis for W. By the way, W, if it wasn't clear, is a two-dimensional subspace of an infinite dimensional space, right? Here's how W was defined, a span of two linearly independent functions. It's two-dimensional. It's got a basis with two elements. That's an orthonormal basis. How does this relate to Fourier polynomials initially? You give me an arbitrary function in the original function space. What's useful with Fourier polynomials leading to Fourier series is to find orthogonal projections of that arbitrary function on a finite dimensional subspace. And your function could be cosine of t, for example. F of t equals, well, it's a new function. It's called h of t equals cosine of t. I could find the orthogonal projection of h along the subspace, call it h hat of t. In the notes, there's the general formula right there for orthogonal projections. Right here, this one in blue. With inner product spaces, where the x's form an orthogonal basis, not necessarily orthonormal. However, if they were an orthonormal basis, this formula simplifies even more. All these inner products in the bottoms of these fractions become ones. Because the vectors have unit length, unit norm. These inner products, where you take the square root, would become 1. So without a square root, they're also 1. And the formula is even simpler. So coming back to the example, call this h1 of t and h2 of t. I would take the inner product of h with h1 times h1 of t plus the inner product of h with h2 times h2 of t where h1 of t is this constant function 1/2 and h2 of t is this funny function. I'd have to compute these inner products, which I'm not going to do by hand, by doing some integrals. I would get numbers, constants. And whatever those constants are, this is the function 1/2, this is the function again, I'll square root of 3/4 times t minus 2. I'd have a linear combination of h1 and h2. It would be a linear function, probably not nice coefficients because of the square root there. That would be the closest function in W to the cosine function. Does that imply anything useful? In the context of Fourier series, and I'll wrap it up with this, you can relate it to nice relationships between graphs. With what you're trying to do with Fourier polynomials and Fourier series is you're trying to approximate periodic functions. And that does mean trying to approximate their graphs well with ultimately linear combinations of trig functions. And you end up wanting to find the coefficients of those trig functions using these formulas that we're talking about involving inner products. That's useful for approximating functions, which is useful, for example, in signal processing. In fact, I'll share a video with you if you know about Veritasium. I think he made a video recently about this. Or was it 3 blue, 1 brown? I'm forgetting. One of those two made a video recently about this. The fast Fourier, something called the fast Fourier transform, which is the most useful algorithm out there in the world. I'm serious. People say it is, at least. It's everywhere. It uses all these ideas. So you can use it for a function approximation, signal processing. You can also use it for partial differential equations, which is what we try to wrap the course up with. You're doing this stuff for concrete examples. That definitely makes it easier. But it still takes practice to work on and get it right. Okay. Have a good day.